Welcome to this explainer. Today, we're taking a seriously mind-bending cosmic tour of the solar system's frozen active worlds. We are going to look at a phenomenon that totally challenges our understanding of planetary geology. We're taking everything you thought you knew about volcanoes and literally freezing it solid.
Okay, let's dive into this. Think about a volcano here on Earth. You're probably picturing glowing red rivers of molten rock, temperatures soaring well over 1,000 degrees Celsius, and these massive, thick plumes of ash just blocking out the sky, right? But what happens when you travel to the outer edges of our solar system? Out there, temperatures plunge to hundreds of degrees below zero, and yet we still see active, erupting volcanoes. So how is that even possible?
Well, the answer is cryovolcanism. Basically, this is the eruption of liquids and vapors, stuff like water, ammonia, and methane, that would normally be frozen absolutely solid at the frigid surface temperatures of these distant worlds. So instead of molten rock, or silicate magma, these bodies are filled with what we call cryomagma. And when it erupts onto the surface, it becomes cryolava.
To really grasp how wild this is, we have to look at the physics for a second. On Earth, regular silicate volcanism works because hot molten rock is less dense and therefore more buoyant than the solid rock around it. It naturally wants to rise up to the surface, pushed along by gases like carbon dioxide and sulfur dioxide. But cryovolcanism? It faces a massive physical hurdle. We all know that ice floats in a glass of water, right? That's because liquid water is actually denser than solid ice. Meaning, on a frozen moon with a solid ice crust, liquid water should naturally sink back down to the core. It shouldn't rise. So how off Earth do we actually get these eruptions?
The secret sauce here is the chemistry. If we compare pure water with an ammonia mixture, things get really interesting. Pure water freezes at 273 Kelvin, but mixing it with ammonia drops that melting point dramatically. We're talking by almost 100 Kelvin. Ammonia is basically acting as a cosmic antifreeze, keeping the cryomagma slushy at unbelievably low temperatures. And here is the crucial part. An ammonia-water mix can actually be less dense than the surrounding ice crust, finally giving it the buoyancy it needs to rise.
And once that cryomagma starts rising, things can get highly explosive. As this icy slurry moves up through cracks in the crust, the pressure drops. This causes dissolved volatile gases, like methane and carbon monoxide, to rapidly exsolve or bubble out of the liquid. If you've ever shaken up a pressurized can of warm soda and popped the tab, you know exactly what happens next. The rapid expansion of these gases completely pulverizes the liquid, blasting it out into the near vacuum of space as this ballistic mist of microscopic ice droplets.
Now, we obviously don't have true cryovolcanoes on Earth, but the physical fluid dynamics do actually have some familiar cousins. For example, in the dead of winter on the shores of Lake Superior, you can find formations known as ice foots. Powerful waves pump freezing water up through cracks in the ice, building up these pressurized icy mounds around active vents. It's not driven by internal planetary heat, sure, but the mechanics of pressurized water erupting through ice gives us a really cool terrestrial window into this alien geology.
And all of this builds a fascinating map of our planetary neighborhood. Ice volcanoes aren't just some rare isolated anomaly, they are everywhere in the cold, dark reaches of our solar system. From the asteroid belt all the way out past Neptune into the Kuiper belt, cryovolcanism is a primary driver of planetary geology. So, let's take a quick tour of some of the most fascinating stops.
Section 1. Ceres, salty domes in the asteroid belt.
Our first stop is relatively close to home, in the main asteroid belt between Mars and Jupiter. Ceres is the innermost known body to show evidence of this kind of activity. When the Dawn spacecraft arrived there, scientists were absolutely stunned by features like Ahuna Mons. It's this isolated, steep-sided mountain that is essentially a giant ice dome. It's surprisingly young, and over millions of years, it's going to slowly flatten out in a process called viscous relaxation. We also found Akator crater, which just gleams with bright deposits of sodium chloride brines. Scientists believe the massive heat generated by ancient asteroid impacts actually melted subsurface ice, allowing these salty brines to ascend to the surface, creating features a lot like Earth's pingos, frozen pressurized mounds of groundwater.
Section 2. Pluto. Red-orange ice sludge.
Let's fly billions of miles outward to the Kuiper belt. Back in 2015, the New Horizons spacecraft flew past Pluto and completely shattered our assumptions that it was just a dead, frozen rock. Pluto actually features massive constructional edifices, like Wright Mons and Pickard Mons,
mountains with deep central pits that look incredibly similar to shield volcanoes here on Earth. But perhaps the most striking feature is Virgil Fosse, a trench where an ammonia water cryolava has erupted. What's amazing here is that this cryolava is deeply stained with a red-orange pigment. These are tholins, complex organic molecules synthesized by energetic radiation acting on methane and nitrogen. So Pluto isn't just erupting water, it's erupting a rich, organic red-orange sludge.
Section 3. Triton, the first sighting.
Now, long before Pluto, our understanding of the outer solar system was changed forever by a flyby of Neptune's largest moon, Triton. This was the true dawn of cryovolcanic discovery. In 1989, Voyager 2 flew past Triton and literally caught cryovolcanism in the act. At temperatures of nearly 400 degrees below 0 Fahrenheit, Voyager photographed active nitrogen geysers shooting miles into the alien sky. Triton's surface is heavily modified by this activity, featuring smooth plains and ring-shaped, caldera-like structures called patrae. These were likely formed by the slow, widespread oozing of incredibly thick, highly viscous, ammonia-rich ice lavas.
Section 4. Saturn's moons, Enceladus and Titan.
Next, we head over to the Saturnian system, home to two of the most famous and dramatically different cryovolcanic moons, Enceladus and Titan. This perfectly illustrates how just tiny changes in chemical composition completely dictate planetary geology. Enceladus erupts a low-viscosity mixture of water and salts. This creates spectacular, highly explosive geysers at its south pole that blast so much material into space they actually create and feed Saturn's massive E-ring. Titan, on the other hand, is a totally different beast. Its cryomagma is a thick, highly viscous ammonia water slush. So instead of violent geysers, it just oozes out slowly, building up massive mountain features and domes over long periods of time. I mean, they even named one of them Doom Mons, which is just awesome.
Section 5. The stakes: oceans, organics, and life.
So, we've seen the mechanics and we've taken the tour. But why does this all matter? We are arriving at the grand finale of this explainer, focusing on why cryovolcanism is truly the holy grail of modern astrobiology. To set the stage, let me read you a recent quote from planetary scientist Tom Northeim. We are finding evidence that the Uranus system may harbor twin ocean worlds. This is based on some incredible cutting-edge research looking at the heavily tilted, frankly bizarre moons of Uranus.
The Uranian moons Ariel and Miranda have wildly fractured, heavily cracked surfaces. Recent models suggest that Ariel used to have an orbit 40 times more eccentric, or oval-shaped, than it does today. That elliptical orbit caused extreme tidal heating. Essentially, Uranus's massive gravity was violently stretching and squeezing the moon. This internal friction generated so much heat that it likely maintained a subsurface liquid ocean over 100 miles deep. The freezing and pressurization of that ocean cracked the ice shell, driving intense cryovolcanic activity.
And that brings us to the absolute core of the issue. Why does this matter for astrobiology? Well, cryovolcanism is essentially inverted volcanism. It acts like a giant planetary elevator, dredging up brines, salts, and potentially organic materials from deep, hidden subsurface oceans, and just leaving them right on the surface for us to find? It proves that you don't need to be anywhere close to the sun to have liquid water. Tidal heating and radioactive decay provide all the energy you need. Ice volcanoes are practically handing us free samples of potentially habitable underground environments.
Because of these profound implications, the scientific community is pushing really hard to go back. In fact, the Planetary Science Decadal Survey recently recommended the Uranus Orbiter and Probe as NASA's absolute highest priority flagship mission. Remember, we've only ever seen the southern hemispheres of these moons during a brief Voyager 2 flyby decades ago. We desperately need a dedicated orbiter to study these fractures, map out the organic deposits, and finally confirm if these twin ocean worlds are still active today.
So the crucial takeaway here is this. Our solar system is absolutely not a dead, frozen wasteland. It is alive, it's dynamic, and it's actively venting the contents of hidden oceans out into the void of space. If these ice volcanoes are churning up liquid water, heat, and complex organics, literally the very ingredients for life, who or what might be waiting in the dark? It's a question that is for sure going to drive the next great era of space exploration. Thank you so much for joining me on this explainer. Keep your eyes on the stars and stay curious.